Section 9.10 is Taylor and Maclaurin series. In this section, we're going to learn a general procedure for deriving a power series for a function that has derivatives of all orders. And what we're going to be doing is forming our Taylor and Maclaurin polynomials that we learned how to do in section 9.7, and then finding the general pattern for those polynomials to create our series. So let's look at the definition of a Taylor and Maclaurin series, and then we're going to start working problems where we find that Taylor or Maclaurin series. Now, a Taylor and Maclaurin series says the following. If f has derivatives of all orders at x equals c, which means you can take the derivative of that function at x equals c for all orders, so the first, second, third, fourth, fifth derivative, all the way to the nth derivative, then the following is called the Taylor series for that function at x equals c. Now notice that this is just a summation. It's implied that we're starting at 0 and going to infinity. So the sum from n equals 0 to infinity of the nth derivative of my function evaluated at c all over n factorial times x minus c to the n. If we were to expand that, would be this series right here. F of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c squared plus all the way down again to that nth derivative. Now just like we saw in Taylor and Maclaurin polynomials, here I can raise this guy here to the first power and put it over 1 factorial. Here I can add an x minus c to the 0 power and put it all over 0 factorial. And we're going to be doing that so that it's easier for us to find the formula, because our goal is going to be to find the series for a function that looks like this when it's expanded out. Now, just like in Taylor and Maclaurin polynomials, if the series is centered at 0, then we just call that a Maclaurin series instead of a Taylor series. So the only difference between those two is that if your series is centered at 0, we call it Maclaurin. As I mentioned earlier, we're going to be finding these series by first finding that polynomial, just like we did in section 9.7, and then we're going to be looking for the pattern that we see when we expand that out in order to find the series itself. Let's go ahead and start with example 1. Example 1 is asking us to use the definition of Taylor series to find the Taylor series centered at c for the function. In section 9.7, remember we made that table to organize ourselves, and this is going to be down to the nth derivative, so usually I just go down to the fourth derivative or whatever derivative is needed in order to find the pattern that we're going to be needing to build the series. So I'm going to make that table and I'm going to take us down to the fourth derivative. This is my given function, f of x equals e to the negative 3x. So we have f of x equals e to the negative 3x, and again I'm going to go down to that fourth derivative. So the first derivative would be negative 3 e to the negative 3x. The second derivative would be negative 3 times negative 3 is 9 e to the negative 3x. The third derivative would be 9 times negative 3 is negative 27 e to the negative 3x. And then the last one, the fourth derivative, would be, well, negative 27 times negative 3 is a positive 81 e to the negative 3x. And now what we're going to want to do is evaluate each one of those derivatives at c, and c is given as 0. So let's find f of 0. Well, that's going to be e to the 0, which is 1. F prime of 0, which is going to be negative 3. F double prime of 0, 9. The third derivative's value at 0, negative 27. And then the fourth derivative's value at 0 is going to be positive 81. Now let's build that polynomial. So this is going to be in general because I could have kept going here with my derivatives. So instead of calling it a fourth degree polynomial, I'm just going to call it p sub n of x because we're just building a polynomial, an infinite one. In section 9.7 we said, okay, in order to build this polynomial it would be this guy here, 1 times x minus, where are we centered? 0, raised to the 0 power all over 0 factorial because that's the 0th derivative, plus negative 3 x minus 0 to the first all over 1 factorial, again still centered at 0, and we're looking at the first derivative, so that's why it's raised to the first power over 1 factorial, plus, and then 9x minus 0 squared all over 2 factorial plus negative 27 x minus 0 cubed all over 3 factorial plus 81 times x minus 0 to the fourth all over 4 factorial plus dot dot dot, because again I'm going to the nth derivative, so I'm just leaving it as infinite right now. Our goal is going to be to come up with the power series, the formula that's going to mimic this particular series. So we're going to say that e to the negative 3x is going to equal the sum from n equals 0 to infinity, and now we'll have to find the pattern. So let's look at what we have here. Recall, this is what happens when n is equal to 0, when n is equal to 1, when n is equal to 2, n equal 3, n equal 4. Well, if I look at those denominators, 0 factorial when n equals 0, 1 factorial, n equal 1, 2 factorial, n equal 2, etc., I notice that my denominator is just an n factorial. The next thing I notice is that I have an x minus 0 to the 0 power, x minus 0 to the first, x minus 0 squared, x minus 0 cubed, x minus 0 to the fourth, and the exponent there is matching what n is equal to. Well, I don't need to write x minus 0 because I know that x minus 0 is just x, but I can write that green part as x to the n, because when n is equal to 0, I'd have x to the 0. When n is equal to 1, I'd have x to the first, etc. Now let's see what else is left. Well, I have all those numbers. The first thing I tell students to do is figure out if you're alternating, if you're changing between positive and negative terms. Well, notice that this guy here is positive, that this guy here is negative, and then positive, negative, positive. So I'm going to ignore the number itself. I'm just looking for the sign of that number, whether it's positive or negative. So I notice I go from positive to negative, to positive, and then negative again, and then positive. Well, if you have alternating terms, so you're alternating between positive and negative. So for your alternating terms, and again what that means is going from positive to negative, what you're going to do, well, you're going to be one of two formulas. You're going to be a negative 1 to the n, or you're going to be a negative 1 to the n plus 1. And it depends upon two things. If the positive came first or the negative came first, and it also depends on where your counter starts. So we're going to have to figure out which one of these is the correct one to use for our particular formula. Now if we look at negative 1 to the n, when n is equal to 0, that would be a negative 1 to the 0, which is positive 1. So I'm going to label it as a positive number. When n is equal to 1, I would have negative 1 to the first, which is a negative 1 or a negative number. When n is equal to 2, I'd have negative 1 squared, which is a positive. Here I'd have negative 1 cubed, which is a negative, and here I'd have negative 1 to the fourth, which is a positive. So it seems like this guy here, this negative 1 to the n, worked in our formula. Well, there's a reason why this one worked and the other one won't, and it's because our counter starts at 0 and we're going positive, negative, positive, negative. Now, if you were to pretend to try the other one is not going to work. If we were to try this formula, notice, and I'm going to erase what I'm about to write down, here at n equals 0, that would be negative 1 to the 0 plus 1 or the first, and that's going to be negative. Well, that's wrong, right? Or here, negative 1 to the 1 plus 1, because again, we're using this formula here, that would be negative 1 squared, and that would be a positive, and well, that's wrong. So that's why this formula isn't working for us, because again, our counter starts at 0, and we're going positive, negative, positive, negative. So if you have a series that is alternating, you're going to have to figure out which one of these formulas here is the correct one for your series. So now all we have left to worry about are the numbers. No longer positive or negative of those numbers, but just the numbers that exist. Now notice when n was equal to 0, the number was 1. When n is equal to 1, the number is 3. Again, not negative 3, because I've already dealt with the negative part. We're just looking at the number itself. When n is equal to 2, it's 9. When n is equal to 3, it's 27. And when n is equal to 4, it's 81. Well, what are those numbers? I'm going to rewrite them right here. 1, and then 3, 9, 27, 81. Well, they look like 3 raised to a power. This looks like 3 raised to the 0, 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. So it looks like what's going on here is that I'm taking the number 3 and raising it to the nth power. This here that I'm going to box in black is the power series for e to the negative 3x. So again, let's look in Desmos to see what we've just done. So if we go to Desmos, what we've done is we've taken a function. So I'm going to graph our function first, and our function was f of x equals e raised to the negative 3x. And that's what that looks like. It's that red function right there. And what we've said is, well, we made a function, I'm just going to call it y, that mimics e to the negative 3x. And it's the sum from n equals 0 to infinity. I can't put an infinity into Desmos, so I'm going to put in a slider. I'm going to call it a. And then I'm going to put the formula we just had, which was negative 1 raised to the nth power. And then we had 3 to the n. And then we had x to the n. And then it was all over n factorial. So now, if I add a slider, and I can make this slider go more than that, but notice, as I'm approaching positive infinity, my blue graph is becoming the red graph. Now I'm going to make this slider go a little longer. We're going to start it at 0, and we're going to go to, let's say, 1,000, and our step will be at 10. Okay, so if I do that, notice as I keep going, and this is getting larger and larger, notice that the blue function is really becoming that red function. So it's really becoming the same thing. Alright, so now that we've looked at what that looks like in Desmos, let's continue on to the next example. Example 2 is f of x equals e to the x, and here I'm centered at 1. Just like we did last time, we're going to make that table, and I usually go out to the fourth derivative to find that pattern so I can make my power series. F of x is equal to e to the x. The first derivative would be e to the x. The second derivative, also e to the x. The third derivative, e to the x. And that fourth derivative, e to the x. Now let's plug in the value. We're centered at 1, so we're going to find the function's value at 1. So f of 1 is e, f prime of 1 is also e, f double prime of 1, e, the third derivative's value at 1, e, and then the fourth derivative's value at 1 is e. Now that we have all these values, what we want to do is build that polynomial just like we would have in section 9.7, with the exception that we're not cleaning anything up. Building that polynomial, we know that p sub n of x is going to equal e times x minus 1, because I'm centered at 1, raised to the 0 all over 0 factorial, plus e x minus 1 to the first all over 1 factorial, plus e x minus 1 squared all over 2 factorial. And again, it's an x minus 1 because we're centered at 1. And then this is because it's the 0th derivative, the first derivative, the second derivative, etc. Next one, e times x minus 1 cubed all over 3 factorial, plus this guy, e times x minus 1 to the fourth all over 4 factorial, and then I'll say plus dot dot dot. So now what we want to do is we want to build that power series. We're looking at e to the x, and e to the x is going to equal the sum from n equals 0 to infinity of, let's find that pattern. Remember, this is what you get when you plug in a 0, when you plug in a 1, plug in a 2, plug in a 3, plug in a 4. So I automatically notice that it definitely looks like I have n factorial in the denominator. And then I notice that I have x minus 1 to the n in the numerator. So x minus 1 to the n, x minus 1 to the n, x minus 1 to the n, x minus 1 to the n. Now, am I alternating? Well, let's look at what's left over. I have e, 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 and e. Well, that's positive and positive and positive and positive and positive. So no, I am not alternating. So I do not need a negative 1 to the n or a negative 1 to the n plus 1. But what's left? Well, it's just e, 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 and E. It's always an E. This is just an E, this is just an E, just an E, just an E, just an E. So it looks like all I'm doing is multiplying this by E every single time. So there we go. We just put in an E. Let's also graph this in Desmos just to see. Notice that this guy is centered at 1, so remember we're going to be centered at 1 for this. Putting this into Desmos, we're going to change this function here just to be e to the x. And then this one here didn't need a -1 to the end, and I didn't need a 3 to the end. I'm going to get rid of those. And then I'm going to make this x minus 1 to the n. And remember, I need an e in front of it. And then it was still all over n factorial. Okay, start us off here. And notice as we go on, the blue, and we can't see it as much because, again, we're centered at 1, but this blue graph is just, it's the same as this red graph that we have here.